so I'm unmuted now, but I wasn't saying anything, so I'm just waiting for people to join the meeting.
Hello, sir.
Hey.
When everybody comes in, may I share my screen to ask you a question?
Yeah, sure. Let me just add some more people.
Okay.
No. Right. Okay. All right, I think we can start. So yes, please share your screen and ask your question.
Right, but I'm not able to. I don't know.
Okay, wait a sec.
How.
I've just got too many windows going here. Give me a sec. I should be able to let you share. It's somewhere. Sorry, just give me a sec.
When I'm trying to share my screen, a message pops up saying that I cannot share my screen while other participants is sharing.
Okay. So try now.
I still cannot.
Okay, I'll stop my share completely. I have a function somewhere that disallows sharing from other people, I think, but I'm not sure. But try it now. I've removed my sharing.
Yeah, probably I will be able to just okay. Second. I don't know how this things work. All right, I got it. Okay. Well, I don't know, like I just don't want to waste time, so
Okay, so maybe we can wait at the end.
yeah.
All right. Okay. So let's go back to our slides here. Okay, so welcome everybody. By the way, I'm going to try to, so the chat, I had a little trouble in my discrete math class where somebody asked a question using the chat, but I never saw it until the very end because the way the windows are working didn't work very well. But I'll try to put the chat here. Okay, maybe. So if you have a question, speak up, and you can try by chat. I probably will see it. Okay, so today I'm going to finish implicit differentiation. That'll be the end of 14.5, and I'm going to slowly start 14.6, directional derivative. Okay, so implicit differentiation again. So last time I did the two variable case. So let's move on now to three variables. We're not going to do more than that. So again, what's the idea? So suppose we have an equation in three variables, in x, y, z. So think something like this: x squared plus y squared plus z squared equals to 1. That's a good example to keep in mind. So you know this is going to give you a sphere, right? So clearly this surface that you get in general is not the graph of a function of x and y, right? So there are points one on top of another, so it's not a graph. But again, the principle is the same. So locally, near all points except some bad points, there are some points where it's not going to work. So if you think of the equator of the sphere here, there's no way that you can zoom in close to these points and see the graph. There's always going to be points one on top of another. So these will be the bad points in this example, but for most points, you will have locally the graph of a function. So locally near all points, equation defines the graph of some function, z of x, y, which you might not be able to write down explicitly, right? So, so what we'd like to do is to, for instance, so here's a motivation for this. So what we're going to do is to compute the tangent plane to a surface at a specific point. Okay? So we know how to do this for the graph of a function of two variables, but more generally now what we're going to do is to develop a formula that will tell us how to do it for a more general surface. So suppose again that you have an equation, and of course, so again think x squared plus y squared plus z squared equals to 1, right? You can rewrite it by putting everything on one side and 0 on the other. So basically you'll have some expression in x, y, z, which we'll call big F of x, y, z, equals to 0, right? So you could do this with this particular example. So let's now, so think that this defines implicitly, so this defines z as a function of x and y implicitly. Okay, so we want to find an expression for the partial derivatives of this function with respect to x and y, right? So if you want if you wanted the tangent plane, I'll get back to that with an actual example soon. You want the partial derivatives to find the equation of the tangent plane. Let me let somebody in. There you go. Welcome. Okay. Okay. So how are we going to do this? We're going to use the chain rule. So it's the same trick that we used last time, but now we have 3 variables. So let's take a look at this. So I have my equation f of x, y, z equals to 0. So I have a function f, which is a function of 3 variables, x, y, and z, okay? And I'm going to underline them. We'll see why in just a sec. And now I'd like to see each of these variables as a function of x and y. So, and I'll explain this in just a sec. So I can view each one of these implicitly for z, right, as a function of x and y. What about this x and y over here? So let's just take a look at this. So think of it this way. So x underline is a function of 2 variables x, y. It just happens to be the function x, right? So that's it. The function y is just y, like that. So you can view it as a function of x and y. It just happens to be just this single variable y. And z, whether underlined or not, is, we don't know. In general, we won't be able to write it out explicitly, but it is implicitly defined by our equation. Okay, so I have my little diagram, so I can apply the chain rule if I differentiate both sides, let's say with respect to x. So differentiate both sides of this with respect to x, and it'll be similar for y. Okay, I won't do it for y. You can do it for yourself. It's a good exercise. Okay, so I'm just gonna take this little diagram here. Place it here. Okay, so this will tell me how to apply the chain rule. So here we go. So if I'm differentiating f with respect to x, right? So I'm going to do this with respect to x. So the chain rule says that partial derivative of f with respect to this x here is computed this way. So it's del f del x. I'll just put an underline here so that you know that I'm talking about this guy here. Del x plus del f del y, del x. Yeah, maybe I should underline it, but del f del z, del x. And since I'm differentiating the equation f of x, y, z equals to 0 on both sides, then of course the derivative of 0 with respect to x is 0. Okay, so I just applied the chain rule, and this is what I get. Now, let's take a look at these guys here. Okay, so as I said, this is just the function x. Yes, okay, come on in. All right. Okay, so this is the function x. So the partial derivative with respect to x is just 1, right? What about this guy? So I'm differentiating the function y with respect to x. I'm going to get 0, right? So this becomes the following. So it's del f del x, and I'll forget about the underline now. It's 1 plus 0 plus del f del z del x. This is 0. Okay? And this is what I'm after. So you see, it's just, I get exactly the same thing as in the 2 variable case. So just solve for del z del x, and what you'll get is this. Del z del x will be minus del f del x divided by del f del z. Of course, provided that at the point you're interested in, this does not become 0. Okay? So this allows you to find the partial derivative of z with respect to x, even though you don't know what z is explicitly, but it's given implicitly by an equation. Then you can evaluate these at the point you're interested in, and you'll get the value you want. Okay? So I'm just going to copy that, paste. I'll be very, very lazy and just do that. And if you do it with respect to y, then it's just that, right? So these are the two partial derivatives that we are interested in given big F, okay? So let's see an actual example. So find expressions for these two guys, del z, del x, del z, del y. If z is implicitly defined by the following equation, so it's x cubed plus y cubed plus z cubed equals 1 minus 6xyz. Okay, so this defines some kind of surface, which is probably rather strange looking, but and notice that, I mean, so a common mistake that you might want to avoid doing, and you'll see why, is to try to solve for z in this thing. I mean, you're going to stay stuck with this for months before you figure it out, okay? So this is no good. You don't want to try to solve for z here at all, okay? So you want to do this with implicit differentiation. So here's how we can do this. I'm just going to use the expressions here, okay? For this, I have to write this properly. So I'm going to rewrite it as f of x, y, z equals to 0. And so you can choose either side, it doesn't matter. I'll choose this side, x cubed plus y cubed plus z cubed minus 1 plus 6xyz equals to 0. This is my big F right here. Okay, and so all I have to do is find the partial derivatives of big F with respect to x, y, and z. So let's just copy this. Okay. Okay, so let's see. So del F, del x, nice and easy, 3x squared plus 6yz. Del Fy, del F, del y, 3y squared plus 6xz. And del F, del z is 3z squared plus 6xy. So by the above, let's go back here. Whoop, sorry. Let's call this like that. So by double star, what I get is that del z del x is minus 3x squared plus 6yz divided by 3z squared plus 6xy, and del z del y is minus 3y squared plus 6xz divided by 3z squared plus 6xy. Bingo. Okay. Now, let's make it even more concrete, if you will. Basically same surface. And so I'm asked to find an equation for the tangent plane to this complicated looking surface. And I want it at the point 0 minus 1 cube root of 2. Okay, so I'm asked to find an equation for the tangent plane for this surface. Okay, so here's how this goes. I'm gonna just copy this. Move on. Okay. And I don't need this. This is the point I want. Sorry. Okay, so tangent plane. If we have a function, so in general, right, if I have a function f and of two variables, right, so the tangent plane at the point x0, y0, how did we find that? The equation was given by this. So you have to go back in your notes, but if you remember the section on linear approximation, and this is what we got, del f del x of x0, y0, x minus x0, plus del f del y at the basic point times y minus y0 plus z0. Okay, so this would be for a function f, tangent plane to the graph of f. This would be it. Okay, but now we have implicitly defined functions. So what do we do? So in our case, it's the same. Okay, so use del z del x and del z del y above. Let's call that this. Okay, at the point you're interested in, and because it's implicit, you need the value of z at the same time. So that's the point 0 minus 1 cube root of 2. Okay, so let's just replace what we're going to find. So let's just compute these values. So del z del x evaluated at 0 minus 1 cube root of 2. I'll just replace in here. So I'm going to get minus, so this will be a plus. 6 cube root of 2. Welcome. Okay, so 6 cube root of 2 divided by 3. So this is 0 here, so this is 3 cube root of 2 squared, which will be, sorry, this is a bit annoying, but 2 over cube root of 2. And del z del y at this point, 0 minus 1 cube root of 2. This will be, I'm using this guy now. That's 0. So that will be minus 3 divided by 3 cube root of 2 squared. Is that okay? Does that look okay to you? Hopefully. Okay, so I'm going to take this. Place this here. Okay. Now again, the equation of my plane. For explicit f, I'll just write it as we usually do. So it's z equals to del f del x at the point you're interested in times x minus x0 plus del f del y at the point you're interested in times y minus y0 plus the value of the function, like that. And so here, what I get for my plane will be this, z equals 2. So my del z del x is given here, 6, sorry, I've got 2 over cube root of 2 times x minus, my point is 0 minus 1, I'll just put it here, 0 minus 1 cube root of 2. So it's x minus 0 plus minus 3 over 3 cube root of 2 squared times y minus 1 plus the value of the function at the point I'm interested in, and that's cube root of 2. Okay, so finally I get z equals 2 over cube root of 2 times x minus 1, I'll just simplify the 3's there, cube root of 2 squared times y plus 1 plus cube root of 2. Hopefully I didn't make a arithmetic mistake here, but that should be the equation of our plane. Okay, so, okay, any questions at this point? All good?
Sir, I have a question.
Yep.
Why are we using del z, del x, if we are interested in finding del f, del x?
Sorry, in finding what? Sorry?
Del f, del x for the equation of the plane.
Sorry, I'm not sure I understand your question. So, okay, so this is the equation of a plane. So okay, so I don't know if this is going to answer part of your question, but the z over here is the variable in the equation of the plane. It doesn't have anything to do with the function z, which is over here, right? Not to be confused. Okay, so if you have an equation of a plane, right? So in general would be, let's say z equals to ax plus by plus c, something like that, right? So what I'm interested in are these values here, right? Does that answer part of your question, or maybe I didn't understand properly?
Part of. It's fine. I do understand.
Okay, all right. Okay. Okay, so unless there are other questions, I think this is it for implicit differentiation. Let me just, recap. Okay, so we're given an equation, big F of x, y, z equals to 0. This will give you, this defines a surface, which is not the graph of a function, but it defines locally z as a function of x, y. So again, good example, think of the sphere. If you take what are you doing? Sorry. Okay. So if you take any point, then locally this thing is the graph of a function. Okay. So if you want the tangent plane to this, you'll need the partial derivatives of this function. Since you don't know z explicitly, you need to use the equation itself to find these values. And what we found is that you can always do that simply by computing these, okay, which have to be evaluated at the right point, obviously. Okay. All right, so otherwise it's basically just the same as if you're given f or z explicitly, okay? Maybe the point here is that it's been a while since you found the tangent plane, the graph of a function even explicitly, so you might want to take a little look at that. But otherwise, once you know these two things, you should be okay. All right?
Yes,
Okay.
thank you.
Yeah, okay. All right, so,
I just had a small question.
yeah.
Why are we looking at del z? Like, why not del x or del y?
Ah, you mean over here?
Yeah, I mean, why did we choose to get rid of the z axis? Why not the x or the y? Like, why are we trying to find z in function of x and y?
Okay, yeah. In a sense, okay. Two parts to my answer. So, by convention, when we look at functions, we look at functions of x and y, right? So z, the z coordinate is the value of the function at x and y, okay? So that's the reason why if I'm given a surface like that, then I'd like to see parts of this as graphs of functions, and graphs of functions are in that direction, okay? This said, you have a good point that it's very symmetric, right? We could actually view here y as a function of x and z. It's just that the thing will be, so this is x, y, and then now we're looking at things that are this way, right? And so this way you could actually compute the tangent plane at so-called bad points in the z direction, but now they're not bad points in the y direction. Does that make sense?
So it's basically just by convention.
Yeah, so right, it's just, think two variables, right? So x, y. When we graph functions, right, we graph them this way, we don't graph them that way, right? I mean, we could, but it's just usually we write our functions as this way, right? So that's the reason why here I'm looking at z as a function of x and y. It's the same reason that here I'd see y as a function of x. But it's, yeah, convention. Basically, you could flip things around and do it in the other direction, no problem.
Okay, good. Thanks.
Okay? All right. So let's move on to 6. So that's the end of 14.5. So 14.6, which will be our last section in chapter 14. So I'm not doing 14.7. After that, we're going to move on to chapter 15 and integrals. So a directional derivative and a gradient. Okay, so let's start with the directional derivative. How much time do I have left? Not that much. I don't want to overload you. So let's start this slowly. Okay, so I'm going to stick to two variables here, mostly. Okay, so if you remember, we defined the partial derivatives. And I want to go back to this. So what was this about? So I have a function f. I look at its graph, which looks like that. Right, so this is the graph of f. So what were these partial derivatives? So I take some point, let's say y0, x0, like that. I look at the point, corresponding point on the graph. And what we did is we sliced the graph parallel to the axes, and we looked at the slopes in those directions, right? So these give us the slope of tangent line parallel to x and y axes. Right? So we found slopes in those two directions. But it'd be interesting to get the derivative in any direction, right? So what about any other direction? I mean, if we can do it in those two directions, in theory, we can do it in any direction, right? So let's see how this goes. So what I'm going to do is just refresh your memory about the definition of the partial derivatives. And then we're going to see how we can modify that to get the derivative in some other direction, okay? So, okay, so partial derivative of f with respect to x at a certain point x0, y0. What is that? That's the limit as h goes to 0 of x0, sorry. F of x0 plus h y0 minus f of x0 y0 divided by h. Right, so I'm just looking at an increment in the x direction. The y direction stays completely constant, and the same in the y direction. This is the limit. H goes to 0. F of x0. I increment in the y direction only. I keep the x direction completely constant, and this is what I get. Okay. But now I'd like to take some arbitrary direction and do the same thing. Okay, so how do we do this? So we have our function f. We have a point x0, y0, and now I'm going to choose a direction. So what's a direction? Well, let's say this is the xy plane, and I have my point x0, y0 like that. And I'm just going to choose a direction. Well, what I'm going to do is just choose a vector, u, that points in some direction like that, and locate it at x0, y0. Okay, so this will be a vector u. Let's say I call its components a, b. Now this would work if you choose any non-zero vector, but there's a scaling issue here. So what you want to do is actually choose a unit vector. So this is a unit vector. In other words, it has length 1. Okay, so that's what a direction is. A direction is given by a unit vector, and you locate it at x0, y0. Okay, so I'll try to draw this. I have the graph of my function like that, graph of f. I have my base point x0, y0. This is the point here. And what I want to do basically is just choose a direction. Let's say the direction is here, like that. This is u. Okay, and I'd like to slice the function above this line, right? So that's what I want to do. Okay, so rather than follow the coordinate axes, I just follow the direction of u. So you see that you get a function. This is the graph of a function of one variable, but it's skewed, okay? So that's the technical difficulty. In terms of defining this, it's the same as the partial derivatives, but in the computation, there's gonna be a difference, and you'll see what happens. But for the definition, it's basically just the same as what we did for partial derivatives. Okay, so let's try it out. So what I'm going to do is basically mimic this, but now in the direction of u. Okay, so to do this, I'll have to find a parametric representation of my line. Okay, so I have a point x0, y0, and the direction u given by AB. So I want the line through x0, y0 parallel to u. I want a parametric representation of this. Going back, eh? Okay, so how does this go again? Well, if I write it the way we saw it, R of t, that's your base point, right, plus t times your vector, right? I'll put that in quotes like that, right? So if you remember how to find the parametric representation of a line, point plus t times the vector, that gives you the direction, okay? So here, what I'm going to get, so I'm going to write R of t as x of t, y of t. So this will be x0, y0 plus t times AB. That's the same as x0 plus t times A, y0 plus t times B. Okay. So my parametric representation, if I wrote it in terms of coordinates, it'll be this. X is x0 plus t times A, and y of t is y0 plus t times B. Okay, so that's my line through x0, y0, which is parallel to u. Okay. Okay, so I have my function f, and we want to restrict it to this line. So how do we do that? Well, you simply evaluate it on the line only, right? So we get a new function of one variable, which I'll call g. Okay, so what is g of t? This is f evaluated on the line, x of t, y of t. So I'll just write it out explicitly. So this is f of x0 plus t times a, y0 plus t times b. Okay, so this is the function whose graph you saw on the previous slide. Let me just go back. If you look at this, right, this is the graph. If you slice above the line like that, you get the graph of g. Okay, and what I want is the derivative of this function at the point which is here. Okay. So we've got g of t is f of x0. Okay, we're almost done with this. Okay, so we want the derivative of g at the point corresponding to x0, y0 in our picture, right? So what is that? Which value? So what is t0 for this? Okay, so how do I get x0, y0, and here's t equals to 0, right? That's what I want. So we want g prime of 0. This is what we're after, okay? This will give us, if I redraw this, I've got this point, I've got my vector u like that. I've got my curve like this, right? So this is the point x0, y0. And this happens at t equals to 0 for g. Okay, and I want the slope of the tangent here. Okay? I know this is a little heavy, moderately heavy, not super heavy. Okay, so I'm just going to finish the computation of g prime of 0, and let's see how far we can go without boiling your brain. Okay, so again, g prime of 0, this will be, by definition of the derivative, this is the limit h goes to 0, g of 0 plus h minus g of 0 divided by h. This is just the definition of derivative. Okay? Now I'm going to use the definition of g to get what I want. So this is a limit, h goes to 0. So what is g of 0 plus h? So this will be f of x0 plus h8, y0 plus hb minus f of x0, y0 divided by h.
So I have a question.
Yes,
Why it's HA and HB?
over here.
Yes.
Okay, so so this is, look at what's inside here. This is h. This is the value of t. So,
All right.
right? So
Okay.
you just replace t by h, basically.
Thanks.
Okay. So, but now just look at the expression which is here. You see that what you're doing is this is the value at the base point, and what you do is you move off the base point by an increment of h in the u direction. That's basically what you're doing. So I'm going to rewrite that in a slightly different form. Just rewrite it, okay? And you'll see better what's happening, okay? So I'm just going to rewrite. Okay, so let's go over here. Okay, by the way, this is what you're looking at is exactly the definition of the directional derivative in two variables. But I'm going to rewrite it as follows. It's a bit cleaner, okay? So I'm going to call the point x0, y0, or I'm going to call this x bar, okay? So notice this, that x0 plus HA, y0 plus HB, what is that? That's x0, y0 plus h times AB, right? So this is just x bar plus h u. That's my unit vector that I chose at the beginning. So this is the limit, h goes to 0, f of x bar plus hu minus f of x bar divided by h. So conceptually, there's absolutely no difference here. It's just a different way of writing it, but the advantage of writing it this way, you see there's no coordinates anymore. So this is actually valid in any dimension. And I think it gives a better idea of what's going on, right? So you look at the value of the function f at your base point, and you move off by a small increment in the u direction. You see exactly what's going on here, okay? So this is called the directional derivative of f at x bar in the direction of that's exactly what you're looking at. Okay, so that's the formal definition. Now, basically, I'm going to stop here, but just to tell you what's going to happen next. Now, question is how to compute. Now, this is not so obvious because now we have increments in all the variables at the same time. So it's not a one variable problem. So the difficulty, it does not collapse to a single variable like del f del x, del f del y. Right? So there's an increment in both components. So there's no trick like the partial derivative trick we saw that you keep one of the variables constant. It doesn't work. But we're going to find a way around it, okay? But there is a simple way around. It's pretty cool. Okay, so we'll see that next time. Any questions about this or anything else? Okay, so tomorrow, in principle, we have a class. What I'm going to do is maybe take 5-10 minutes to show you the answer to this. Okay, so tomorrow it should be take 10-15 minutes. Insert to the above. And then if you have questions, there will be a problem session, and we'll see if we can share screens. I think I see how to do it simultaneous where everybody can share at the same time. But anyway, so if I have other questions.
Could you just go up one screen so I can see what you wrote? Thanks. No, that's two screens. Yeah, thanks.
I have a question.
Yes.
Will we have more web work since we can't really do quizzes?
Yeah, I'm going to set another one up fairly soon. The other thing I'm going to do is, I mean, this will not be for grades, but I'm gonna send you the quizzes you would have had had we been in a normal situation. I'm gonna send you the quizzes which you can try out, and I'll send you the answers also. But I'm gonna try to set up some. I have at least one other web work coming up, but maybe if I can figure out some new ones, I will. Yes.
Thank you.
All right. Okay. So, okay, again, I'll post the video and the notes. Sorry, I haven't edited the video, so you have to skip the beginning where nothing happens. If I have a few minutes, I'll try to edit them. But anyway, okay, hope you're all doing okay, and I'll see you tomorrow afternoon, I guess. Oh, it's at 2 o'clock, right? Okay, I'll have to check. Okay, so see you guys.
Sorry?
Yeah.
May I try now to share my screen to see if I can ask you the question, or would you prefer tomorrow?
Just give me one little sec here. Yeah, sure, go ahead. Aha.
Works this way. But this is the question. Actually, it's a question in the book, the 6th edition, 14.5, number 51. Well, the question here is the above. If z equal, if z is a function
Yeah.
of x and y, where x equal r square plus s
Mhm.
square and y equal 2rs,
Yep.
find del 2z del r del s.
Yes.
So I computed this way and the answers turned to be wrong, and I don't understand why.
Okay, so this is basically the same thing that this is very, very similar to what I did, right? In the example I did last time. Okay, let me
Yes,
see.
exactly.
Okay, let's see. So del z, del s, del z, del x, del x, del z, del y, del s. That's 2s. Yes, yes, that looks fine. Then del r of this. Be del x of okay, so let me just try something. Where's my wait. Okay. Yeah. So this part here,
Mhm.
can you see? Oh, it disappeared.
Yes.
Okay. So you want, okay, so you're differentiating this with respect to r. So the first part, you'll have to use a product rule, right?
The first.
When you do the partial derivative of this with respect to r, actually, no, you can factor out the 2s, but what happened to the 2s here?
The answer was really similar to mine, but it has an additional 2 del z del y, I believe.
Okay, so here's my question. My question is, I'm looking at, draw. I'm looking at, so, why isn't it, this is not working. Wait a sec. Draw this, okay. This guy here. So you're computing the partial derivative with respect to r of this whole thing here. Can you see my cursor?
Yes.
Okay, so then I mean, where did the 2s go? Because when I'm computing the partial derivative of this with respect to r,
Mhm.
I should be getting,
Because when I did of del z del s del r, I just did like the chain rule. Because
yeah, but the 2s, which is here, where is it? Where did it go?
well, on the fourth line, like where it begins to write in blue, like there is the 2s.
Okay, sorry. I absolutely see what you're doing. This is, okay, absolutely, sorry. Everything is good. Okay, so del x of this times, no, wait. Okay, here's the problem. The problem, so del z del s is a function of r and s, right?
Yeah, right.
And you're differentiating with respect to r, so there's no chain rule at this point.
So I just have to put it like directly in. Like,
Yeah, so it's the partial derivative of this with respect to r. you'll have to use a product rule here. The sum is fine, product rule. But it's when you get to this part, when you'll get del R of this guy, then you'll have to use a chain rule, and the same here.
So in fact, like the way that I shall do it is like this. Just put del R here.
Yes. Ooh, you're good.
I don't know, like I have just discovered. and here, so it's a like just find the derivative of this. Like I apply chain rule here.
It'll be, yeah, the chain rule will be applied further down, right? So it's a sum, so you can split up the sum. Then you'll have a product. You'll apply the product, although
Here's
this
the
is,
product rule.
and here also. And once you've done that, then you'll have del R of this guy. Now you have to apply the chain rule at that
All right, I
point.
understand. But here there is no product rule, right?
No, it's just a constant. You can
A
factor out the
constant.
constant. Yes.
All right, I understand. Okay, thank you, sir.
Super. All right, great.
Okay, have a great day.
Same to you. Thanks.